History of Vectors, Episode 3, From Imaginary to Complex. You are here. Hey, it's old Doc Euler. Welcome back. In the last episode, we discussed how this guy, Cardano, used algebra to identify and then manipulate the square root of -1, or in his case, the square root of -15, in the year 1545. Cardano noted with some wit that there didn't seem to be anything of interest on the far side, okay? No obvious mathematical truths and no apparent applications. Okay, in this episode, I'm going to narrate the trek across that desert to the point where we do start to find interesting and useful stuff. Spoiler alert, I will tell you that Euler defines the symbol lowercase script I for the square root of -1 in the year 1777, some 232 years after Cardano's Ars Magna. And it is Gauss who coins the phrase complex number 50 years after that in 1831. Okay, let's get started. The first oasis we will stop at is that of René Descartes. Descartes is one of those people who is famous for multiple things. As a philosopher, his most famous quote is cogito ergo sum, or I think, therefore I am. He is just as famous as a mathematician and is traditionally credited as the inventor of analytic geometry. Cartesian coordinates are named after him. You can see here, if you get rid of the DES, what you're left with is the root word of Cartesian. Someday I hope to do a series on the history of analytic geometry, but not today. Okay. Descartes considered himself a philosopher first. As the mathematical historian Carl Boyer wrote in this book on the right, History of Analytic Geometry, René Descartes was a philosopher who found in mathematics a basis for rational thought, as of course did the recently rediscovered Greeks. If analytic geometry may be loosely defined as the combination of geometry and algebra, Boyer informs us that Descartes did not respect these two branches equally. He was very much a geometer, where geometry is truth and algebra is merely number. And his primary intent was to demonstrate how the craft of algebra could be put to the service to the art of geometry. In retrospect, things haven't worked out that way, but that's a story I will have to tell elsewhere. Descartes was aware of Cardano's work, by this time nearly a century old. Descartes investigated his strange numbers in an attempt to find a geometric interpretation. What follows is an example that is not quite what Descartes did, but is pretty close, although it is written in modern terminology. Today it is known to virtually all students of Algebra 1 as the running for the bus word problem. Consider these two quadratic equations, both of them of the form ax squared plus bx plus c equals 0 in modern notation. They differ only here, the 3 here and the 5 here, but the difference is you get pretty different results. Here you get two real roots, and here you get two what we today call complex roots. These equations can be used to model the following generic word problem. Okay, a city bus starts to pull out of a local stop. Initially it has 0 velocity, but it accelerates at a slow but constant rate. A commuter who is late for the bus and still some distance away from the bus stop sees it pulls out and begins to sprint at a constant velocity with the goal of catching it and banging on the side of the bus to get the driver to stop and let him on. At first, the man is moving faster than the bus and thus gaining on it, but the bus is speeding up. If x is a measure of the distance between the runner and the bus, what is the position measured from some arbitrary point at which the runner catches the bus? Algebraically, at what point does the variable x equal 0? Well, we can't actually solve this problem because I haven't given you enough details, but the solution is beside the point. What's important is that for the first equation, where c equals 3, the plot of the equation y equals x, the blue line, crosses the x-axis twice. And where it crosses the x-axis, those are the roots, in this case the solutions. The first root, -3 from some arbitrary point, can be interpreted geometrically as the point where the runner catches up with the bus. At this point, the person is still moving faster than the bus, so if he doesn't get on but keeps on running, he will pass it. The bus then is still accelerating, so it will eventually catch up with the commuter and pass him. So geometrically, you can visualize a physical meaning for each of these two roots. The plot of the second equation, represented by the orange line, has the same shape as the blue line, but it is offset vertically. As a result of this shift, the orange line never crosses the horizontal axis. Today, we would say that there are no real solutions. The man never catches the bus, presumably because he was too far away when he started running. What Descartes noticed in his version of the second equation, which of course took place before there were diesel-powered commuter buses, is the following. The first term, or the real component in today's terminology of both routes, happens to represent the point of closest approach, where the person stopped gaining on the bus and started falling ever further behind. The man's position at this moment, -2, can be geometrically interpreted as the spot in the road where he came closest. But what about the plus or minus 2i terms? How do you interpret them geometrically? In the end, he gave up. And this is important. René Descartes gave up. He concluded that this algebraic equation could not be expressed geometrically. In this light, as a geometer, Descartes referred to these roots as imaginary, a term that we still use today, although he used the expression for the entire number, what we would today call a complex number, rather than just for simple multiples of the square root of -1. This was in 1637, 93 years after the publication of Ars Magna. Crossing this desert was hard. The next stop in this journey will be with Abraham de Moivre, a French Huguenot who moved to England to avoid religious persecution and ended up hanging out with guys like Isaac Newton and Edmund Halley. One of de Moivre's mathematical achievements is the theorem that bears his name, which links complex numbers with trigonometry. This theorem is little known today because Leonard Euler, some say the greatest mathematician of all time, upstaged him with a more general version some 40 years later. Still, this was a powerful and important result, and one of the very first applications of complex numbers. While it had little practical utility at the time, it had a major impact in academics. It allowed mathematicians to prove some totally new trigonometric identities. All right, considering what we know today about the complex plane with its real and imaginary axes, it is important to state that neither de Moivre nor Euler thought about these expressions in geometric terms at all. To both of them, these expressions were purely algebraic and in one variable, x. Here he is, the man, the myth, the legend. How many people have you heard of who have a number named after them? If you don't know, I'm talking about E for Euler, the base of natural logarithms. It is an irrational number with a value of approximately 2.718. I'm not going to give a biography of him here because it would take all day, but I will say that if it involved mathematics in the 18th century, Euler was probably at the center of it, and the square root of -1 was no exception. First and foremost, it was Euler who assigned the symbol lowercase script I for the square root of -1 in the year 1777. Chronologically, this contribution came last, but I'll gloss over that. Despite his more algebraic bent, he was no more fond of imaginary numbers than the man who coined the term, Descartes. In 1770, he wrote, "All such expressions, such as the square root of -1 and the square root of -2, he wrote them out numerically like this, are consequently impossible or imaginary numbers since they represent the roots of negative quantities. And of such numbers, we may truly assert that they are neither nothing, nor greater than nothing, nor less than nothing, which necessarily constitutes them as imaginary or impossible." Note that this was an arithmetic objection, not a geometric one. What is especially clever about it, as noted by author Paul J. Nahan, is that Euler here is quantifying another unusual aspect of imaginary numbers, that they do not have what's known as the well-ordering property, which, among other things, states that every real number is either larger than, smaller than, or equal to every other number. You can put them in order. You cannot do that with imaginary and complex numbers. For Euler, creating a symbol to represent the square root of -1 was simply a means to an end, and in fact, one he did rather late in his career. That end was to reformulate how what we call complex numbers today are expressed. The method used for centuries to represent these numbers following Cardano was of this form, a plus the square root of b, where b was a negative number. What Euler did was to express complex numbers in the form that we know today, c equals a plus ib, where a and b are real numbers, and as noted, I refers to the square root of -1. You might note that what Euler tacitly did here is to redefine the term imaginary number in a way that is slightly different from what Descartes did. Now imaginary just means pure imaginary, not complex. All right, there's two things that I want to point out about the definition of Z. The first is, as noted, it is comprised of two parts, one purely real and the other purely imaginary. This is a subtle but important taxonomic definition. Second point is that while Z has two components, mathematically it can be considered to be one number, a single mathematical object. And since it is a standalone mathematical object, according to Euler, we can define its properties, its being singular. We will go over these properties in the next episode. Even Euler's defining Z equals a plus ib was only a means to an end for him. It was in 1749 that he made what is arguably his most important contribution to complex analysis. In today's terminology, he proved that what we today call the set of complex numbers is closed under essentially all algebraic operations. This means that any mathematical operation you can do on any combination of complex numbers, such as, but not limited to these, will produce another complex number of the form a plus ib. Remember that the way we got into this mess was because we found that real numbers failed this test. The square root of a negative real number produces something that's not in the set of real numbers. Okay? There were several mathematicians at the time who argued that mathematical objects other than multiples of 1 and multiples of the square root of -1 would be required to express quantities such as, say, I to the ith power, but they turned out to be wrong. This is a big deal, both to the math guys of the time and to us today. It means essentially that complex numbers behave themselves surprisingly and remarkably well. In fact, better than real numbers. Algebraically, if not geometrically, this kind of hints at the idea that complex numbers may be more real than real numbers. Okay, but that's metaphysics and we're not going to go there. We are not quite through the metaphorical imaginary desert yet, but we have made a lot of progress. Here are some dates for a timeline to indicate how long each stage took. Okay, 1545, Cardano considers the square root of a negative number. 1637, René Descartes coins the term imaginary for these numbers that have no known geometrical interpretation. 1707, de Moivre finds a relationship between imaginary numbers and trig functions, a result that keeps mathematicians busy for quite a while. In 1748, using Taylor series expansions, Euler publishes his work on one of the most well-known and useful equations that we have, Euler's formula, right up there with the Pythagorean theorem and the quadratic formula. Euler does more stuff, coining the term I in 1777 and formalizes most of the algebraic properties of complex numbers that we know and use today. Okay, this is not the end of the story. We still have a ways to go before complex numbers become a mandatory subject for engineers and scientists. That really sort of comes in 1887 when Tesla patents his AC motor. The math for calculating the phase differences between AC voltage and AC current are much easier with the introduction of complex numbers and Euler's formula as practical shortcuts. So a bit of foreshadowing. After the math in a paper by a Norwegian named Wessel in 1799 is recreated by Gauss in 1831, we finally get to a sort of geometric interpretation of complex numbers. It is this, the concept of the complex plane, that goes on to become the first vectorial system. Okay, that's it for today. But before I continue with the history of vector analysis, I need to spend the next episode discussing the algebraic properties of complex numbers now that Euler has thrashed them out for us. Algebraic properties of complex numbers. Okay, perhaps a shiver of dread just went up and down your spine because you know it's coming. The commutative property, the associative property, and all that tedious stuff that you thought you were done with when you left 7th grade behind. Okay, in my defense, algebra doesn't have axioms the way geometry does. It has properties instead. So the troubled physics major has to be aware of these properties. Okay, more importantly, for our story, this will lay out the groundwork for why vector analysis turns out to be so weird. Okay, don't worry, it'll be fine. Old Kohler is here to guide you through. So see you then.